Your agent crashes halfway through a customer request. It classified the issue, found two facts, drafted a response, and then stopped. Now what? Start over and hope it chooses the same path? That is the problem LangGraph is built to make explicit. A graph workflow names the state, names the steps, and names the routes between those steps. In this lesson, we will build the mental model with deterministic Python. State, nodes, edges, conditional edges, reducers, compile, and invoke. Start with state. State is the shared contract every node reads and updates. Here, support state carries the request, customer tier, route, facts, draft, risk score, final answer, and history. Node result is the patch a node returns. This is important. Nodes do not need to rebuild the entire state object. They return the fields they own. If risk matters later, make it a field. If facts matter later, make them a field. If you hide those decisions inside freeform text, the next step has to rediscover them. A node is just a unit of work. In LangGraph, that node might call a model, invoke a tool, retrieve documents, or run ordinary Python. The rule is the same. Read state, return an update. The classifier writes the route. The policy node adds facts. The draft node writes a draft answer. The risk node writes a risk score. Notice the boundaries. The classifier does not also finalize the answer. The risk node does not also retrieve policy. Clear node ownership makes the graph easier to test and easier to debug. Edges are the control flow. Normal edges are simple. After classify, go to retrieve policy. After retrieve policy, go to draft response. After draft response, go to review risk. Then the graph reaches a conditional edge. Review risk has already written the risk score into state. The branch function reads that score and returns either finish or escalate. This separation is the useful part. Nodes compute, edges route. When those concerns blur together, the graph becomes hard to reason about. Reducers decide how updates merge. Some fields should overwrite. The current route, draft, risk, and final answer are scalar fields, so the latest supplied value becomes the value. Facts and history are different. They accumulate. If classify finds billing language and retrieve policy finds the invoice requirement, we want both facts. Losing the first fact would make the final answer harder to explain. That is why reducer design matters. Last writer wins is fine for some fields, but dangerous for evidence, warnings, citations, and execution history. Now run the demo. The billing request visits classify, retrieve policy, draft response, review risk, and finalize. The route is billing, the risk is 0, and the final answer includes the facts used. The security request follows the same structure, but writes a security route and an MFA reset fact. The escalation case is the branch to watch. Urgent enterprise language raises risk, so the conditional edge sends the workflow to escalate instead of finalize. The visited path tells us exactly what happened. The tests are where graph design becomes concrete. First, assert the path. A billing request should end at finalize, not escalation. Second, assert the branch. A high-risk request should reach the escalate node and skip finalize. Third, assert reducers. Facts and history should append, not disappear. Finally, test the guardrail. If a graph loops forever, invocation should fail loudly instead of running until someone notices the bill. Here is the interview version. State is the shared contract for the workflow. Nodes are focus functions that read state and return partial updates. Edges decide which node runs next. Conditional edges choose a branch based on state. Reducers define how updates merge. Some fields overwrite. Other fields, like facts, citations, warnings, or history, should accumulate. A strong answer also mentions testing. You should test paths, branches, reducer behavior, and loop limits separately from model answer quality. The goal is not to make the graph clever. The goal is to make the workflow inspectable. Use type state for decisions that matter. Keep nodes focused. Make branch conditions small enough to explain. Choose reducers deliberately, especially for evidence and history. Once those pieces are clear, LangGraph gives you a durable way to build agent workflows that can be resumed, tested, traced, and improved.